I don't have a. Oh, how am I going to record? There's no.
There's the
Video.
cameras are up here.
It doesn't let me. Cannot start video. Oh, I got it. I got it. Oh, that's the camera. Why didn't it work? Stream it up. Press that. Select the course name. Oh. Danielle. Okay.
They're making fun of your
videos and videos. Just stop.
Yeah, but you know that my know that they're not.
Oh, do we need? Okay. Do we have to show before?
Have your own? Not anymore.
What is the stream?
What? It's the next thing of always
They're canceled like for good.
Until
the next day.
They've always taken them away.
I'm
saying
the next
they're
study comes out for now.
And they do.
On the
yeah,
apparently
North
North
Korea
Korea
is like South
That's for the fifth year.
It's a good time. They're like 20 times. Yeah, so we want to just like
To the plane.
Like they're all like got it.
I mean, they're still like
I'm not
apparently so that you didn't need to start at 6:40. And the person yeah, you need to start at 5. Just notes that you don't actually it says on CDC not the
Going already?
And she was like, oh, just put that. Let me put that in a second. And
I think I'm gonna fall so behind. I just like can't spend every minute.
I've been like,
Also, your sister. My sister too. No, me and my sister. Like, my sister. Just really. No, so until Sunday, like I wasn't work. It's not great. I'll just like no stuff last time. I'll do it last year. I remember being very confused for the.
I'm saying that I don't know the gap.
My phone's already dropped out for next year.
It's like not enough.
I tried, but
It's so
video
Yeah, so what is it? How much count two? It's like more like count two.
yeah. So count two is probably more like the count of eyes.
It's multi. Yeah. It's in America. Oh, it's because people. It's like I would have been taking.
I just changed the video camera. Under here. Thank you. Your divine influence.
My presence helps you
Exactly.
find the solution.
All right, so we're recording, and yes, did anybody log in from?
You want it open or closed?
It doesn't matter.
Do we have time?
Sharon Foxman.
Funny answer. That's it's not trendy. It's not trendy. Like it's so so yeah. It's really going.
Okay, so we'll start now.
It's like stop getting it. No one else.
Sure, Sharon. Come over.
Share screen.
I'm pretty sure I had it, but I didn't have it. Love that thing. Do like the first couple.
Okay, so so as you can see, I'm not. My name is Nachman Danzig, and this is a course called Computer Architecture. It's sort of connected to the lab, which is also Computer Architecture Lab. In that class, you're going to learn assembly, programming. Here, we're not going to really learn the programming, but I'm going to talk about the programming a little bit because that just sort of gets you into the idea of what a computer does. So the purpose of the class is to explain how to design a computer in a hardware sense. In other words, you learned a course called Digital Systems, right? You all have to remember that course because we're going to build on that course. We're going to take, although you don't have to remember, not to scare you too much, you don't have to remember all the details of that course. You just have to remember some of the basic ideas. That there are wires that pass bits, that there are, and then the different, let me take my mask off actually. The different elements. So anybody remember some of the elements that you built? Now, it's not obviously AND gates and OR gates. What did you build with those things? Multiplexers, adders, decoders. I don't know if you remember what a decoder. Flip-flop. Well, flip-flops, yeah.
Registers,
Right.
counters.
Registers. So all those things that you're just saying, now we're going to use them as Legos to build a computer, as pieces to build a computer. That's the ultimate goal. But we're not just going to, that's just part of the course. That's the most interesting part of the course. How to build it is also like basically, what does it mean how to build it? How to build it in a way that we can get our programming commands to work, right? We have a command, like the most basic command is adding two numbers. How do you get that to work? Or other commands are for, we're going to learn like jumping from one line to a further down the code. Because if you think about, let's say you have an if. Say if something is true, then do this. If it's not true, then jump down 10 lines and do something else, right? So you have to, that's called a jump. So how to build all of those features into the computer so that the computer can actually execute your C++ program. That's what we're going to do. So it's actually a quite interesting course. Now, these slides, there's a new subject this year which we added on, which is a very important subject, and I'm happy we're adding it on, but it's not yet in my slides. And that's pipelining. So these slides are from last year, but so some of them I left off. One set of slides is removed, so to make room for pipelining. Anyway, now
What
here.
What is computer architecture in Hebrew?
מבנה המחשב.
מבנה המחשב.
So this is for the lab. I can skip this obvious teaching in the lab, I think. Is that what? Oh, why is this? This is okay. This is all for the lab. But here, I want to start. The way I teach the course, I use the same slides from the lab because you need to get into the subject in the same way. So that's why you see here. Okay, so the computer understands something called assembly language. You have written in a high-level language. A high-level language, does anyone know what a high-level language is? What does that mean? Yeah, but that's an example. But what makes it a high-level language?
It's common. It's going to be compiled.
It's going to get compiled and into what? Into machine language. It's going to be compiled into machine language, and then the machine will understand it. Why is it called high level? Why is it called just?
Because it uses our language.
Yeah, it uses our language, but because so we're high. We're like, because if we would use chimpanzee language, it would be. Why is it called high? In what sense is it high? You're right. It uses our language. But why is it high? High is in the sense that it's far away. It's above the architecture, the machine. Low level is close to the architecture. So low level commands, it's like driving a car in a manual, as opposed to automatic transmission. So okay, machine or chip. The machine or chip is hardwired to understand one set of instructions. This is called the machine language, or it's also called a chipset. In other words, there's a chip. There's different chips. For example, there's an AMD, and there's an Intel, and there's an Apple, and there's a chip on an Apple phone is a different chip than an Apple Macintosh. So those different chips actually have different machine languages, different architectures. They work in different ways, and therefore the way you talk to them is different. That's what it means. So writing in this language would mean writing like this: 1 1 0 0 would be ones and zeros. That is the only language the computer can understand ultimately. An assembly language is a translation of these binary commands into more human or English format. So first, the lowest level is the ones and zeros. We can call that the machine language. Then the assembly language is one step removed from that. It's still a low-level language, not a high-level language. It's a low-level language called assembly, which is a translation of this command. Like this command might be add register 2 to register 3 and put the result in register 4. That might be this command. Add the value in register 1. Everyone knows what a register is. Something that stores a number. So add the number in register 1 to the number in register 2 and put it in register 3. That might be this command. Now it's if you're really into numbers, then you might memorize that. But you might find it easier to write the word ADD. Add, register R1, R2, R3. It might be easier for you to write in that kind of language. That would be called an assembly language command. Although that language would be translated into machine language by something called the assembler. The assembler takes the assembly language and puts it into machine language.
So C++ is not assembly.
And C++ is a high level language, different thing.
So
Beyond, it's up higher than assembly. Yeah.
So what is assembly language?
Assembly language, well, we're going to see examples, because that's what we're going to talk about. There's a one-to-one, so what's the difference between C++ and assembly language? C++, you might do a command like A equals parentheses, B plus C plus D, parentheses divided by parentheses, D divided plus, Q, and it could be a very long command. That's one line in C++. In assembly, there's no such complex lines. Every line is either add, divide, two numbers, it's always two numbers, not three. And it's much more basic. Therefore, one line of C++ might be many lines of assembly in a translation. But assembly into machine language is a one-to-one translation. Every command of of assembly can be translated directly into this ones and zeros. And in fact, you're going to learn how to do that. I'll show you how to do that. Although I think also Avi would. There's a kind of overlap between the two courses. Avi might show you that also. But it's probably good for you to hear it twice. Yeah. So now a little history. Oh, somebody asked a question about C++. Well, am I going to get to C++? I'm going to show you examples of C++ and an assembly. When were assembly languages first invented? I'd like to give a little history. So the first computers were not programmable. What does that mean, they're not programmable? Can you think of it?
It just did the one thing I was given.
Yeah. So what would be an example of a non-programmable computer today? Calculator, a handheld calculator. You press the plus button and it does plus. That's it. You can't make the plus do something else. You can't, calculate pi, you can't do calculations other than adding and subtract. Whatever is written on the keys. It's like if you all watch old Star Trek TV show, they had computers, they didn't have keyboards. They just had buttons. In other words, you press this button and it does that action. This button does that action. Every action that you could ever want is there. If you want a new action, tough luck. You got to build a new computer. That would be the first computer. And actually, every program that you have written in C++ could be built in hardware. It's a fascinating idea. Every program that you've written, you could build hardware that would give you the same results. And in fact, computer programming is one subdivision of electronical engineering. They said, okay, you could also build a computer that you can program, and then you have to program it. But why do that? Just build the computer. And every time you need a new solution to a new problem, build a new computer.
You have to send out a new piece of hardware.
So obviously there's a big problem with that. You have to build a new computer every time you need something new. If you can anticipate everything you'll ever need, then you could do that. But what if you have a new need? Like on a spaceship. You actually are not going to program the computer on a spaceship usually. Maybe nowadays they are, but pretty much the astronauts are not expected to be computer programmers. So somebody built a hardware that does everything they need, and they just press the buttons. Or in a jet fighter plane, you don't program it while you're flying it. You just press the buttons that are there. Okay, so those are the first computers. They were not programmable. They were calculators. Think back to your course on logic circuits. Okay. The hardware determined the whole range of functionality. That's what I just explained, right? The whole range of functionality is built in. There's no new functionality you can add. Where are we? It's weird. Then there were programmable computers. The first ones were in like 1944. They were actually at the end of World War II. They were building them. They needed computers for, for battleships, let's say, to compute the trajectory of a missile, which angle to shoot it at, how the wind is. Anyway, programming done on machine-specific machine language, right? So once you have a programmable computer, you got to write a machine language. One of the first computers was called a Mark I. It was called that by the Harvard University staff. It was actually called this, automatic sequence controlled calculator. See, it was a calculator, but it was controlled, programmed, a programmable calculator by, I don't know, by sequence, whatever. It was a general purpose electromechanical computer. That means there were mechanical parts to it. It moved. In other words, things had to move in order to do things. It was actually used in the Manhattan Project, the Manhattan Project to create the atomic bomb. They actually used this computer. Another programmable computer was called ENIAC, Programmable Electronic Computer. It was at the University of Pennsylvania. Okay, these are some of the early computers that were programmable. Now I'd like to talk about this. Actually, before you get there. So these, in general, these were in machine language, which means ones and zeros. Now, now it comes, well, I don't know how to make this suspenseful or not, but I'll ask it so that you'll all answer correctly. The person who, first of all, who thought of writing in assembly, in other words, add A plus B plus C as opposed to 11001, was that person who came up with this idea a man or a woman?
Woman.
A woman.
I'm gonna say woman.
So basically, there was this woman who you can actually see her. What? You can actually see her on YouTube. Now she's long since deceased, but she made it to 60 Minutes or YouTube, so you can see her on YouTube. Her name is Grace Hopper, and they call her Amazing Grace. Amazing Grace, like the song Amazing Grace. They call her Amazing Grace Hopper, and she was a professor of mathematics, and when World War II broke out, she decided to join the Navy, and she came there, and they sent her to she's a mathematician, so they sent her to the programming department in the Navy, and she came there, and she saw all the men writing ones and zeros, and she said, "This is ridiculous. Let's make up a language." And they said, "Yeah, and you're going to have to write a program to change that language into the ones and zeros." Because it's not in the end, that's ones and zeros. So you're going to write that. You're going to have to write that. We call that a compiler, we call it an assembler, really. It's like a compiler. We call that an assembler. You'll write that. She said, "Don't worry, I'll write the assembler." So she didn't just come up with the idea, she actually implemented it. She wrote an assembler in ones and zeros to change her language that she invented, her assembly language, into machine language. And that was like a revolutionary idea. She then invented one more idea, which is even more amazing, which is she invented high-level languages. What is a high-level language? The real way I like to call high-level language is a machine-independent language. What do you think I mean by that, machine-independent language? Yeah.
It doesn't matter what machine it's on.
Exactly. It doesn't matter what machine it's on. C++, I can write the same code in C++ and run it on my cell phone or run it on my laptop, even though they're completely different chips, completely different machine language. So the high-level language is independent of the underlying hardware. And that was her idea also. In other words, she said, well, once we've got this add, let's invent a theoretical language that could be anything. And as I'll write a theoretical language, and then I'll just write a compiler to translate this theoretical language into the actual language of the machine. Now, of course, if I'm going to write C++ for my cell phone and for my laptop, how many compilers do I need? I need two different compilers. I need a compiler that knows how to translate C++ into the machine language of my cell phone, and another compiler to translate it to the machine language of my laptop.
Wait, a compiler and assembler are different?
Yeah, assembler just takes the one-to-one language and translates to machine language. It takes.
So you need a compiler, and then a compiler loves the assembly.
Wait, you need the compiler takes a high level language and converts it into machine language.
So you need a.
You don't need to go in steps. The compiler can convert directly a high level language into the machine level language. You could say it like that. Some people like to say it that way, that it converts into assembly and then assembly into that. But that doesn't make sense to me. The compiler takes the high level language and puts it in a machine language.
And what is it?
And an assembler takes the assembly, the low level human type language, and puts it into ones and zeros. The compiler also puts it into ones and zeros. But the compiler takes an abstract language like C++, a language that is not connected, abstract in the sense it's not connected to any particular hardware. Whereas assembly is connected to a hardware. If you say, I learned assembly, you're speaking the truth, but not the whole truth, because you have to specify which assembly you learned. The assembly for an 8051 chip is different from the assembly for a MIPS chip. Every chip has its own assembly. So you have to say, I know assembly of MIPS. Now, it turns out that the assemblies are very similar between so once you know one assembly, you can easily learn another one. But there's no such thing as assembly language. There are assembly languages. Okay, that's enough of that. Characteristics of assembly: there's an extremely small set of commands the chip can understand. From these, you need to build your program. The assembler translates your human assembly commands into machine code. Why should we learn this? So I like to say it's like driving a car in manual. You know exactly what you're doing instead of just letting things work. Gives complete control over the final machine code. High-level languages are also compiled into machine code eventually. That's what a compiler does. But they will contain a lot of inefficient code. The compiler compiles your high-level language into machine language. But in order to make sure it works, you may end up with extra lines of code that if you would write directly in assembly or machine language, you could eliminate. And you could therefore make the program run faster. So if you're doing, let's say, high-frequency trading on Wall Street, and every millisecond is important, you might want to write your program in assembly so it'll run faster. Furthermore, if you're writing a automatic driving program for your car and you want to be able to detect that somebody just ran in front of the car, you want to do that quickly, you might write it in assembly. And in fact, Mobileye writes or did write in the assembly that we're going to learn. There is actually a new, more than there was 15 years ago or 10 years ago, there's more demand for assembly programming because of all the need for auto driving cars and things like that. So it'll run faster. It's useful when extremely high speed or small space is needed. For example, a spaceship program you might want to write in assembly because you don't want to have extra memory that you want to use. You don't have extra. You want everything to run efficiently. High frequency trading. And then a third reason is to be a professional, you need to understand the underlying working of your program. In other words, if you really are going to be a professional programmer, you should know the whole thing, what you're doing. Okay. Now what we're going to learn the MIPS instruction set. MIPS stands for microprocessor without interlocked pipeline stages. You don't have to remember that, but that's the name of the chip that we're learning. It is a reduced instruction set computer called RISC. And there's something called CISC, which is complex instruction set computer. Reduced, it means not complex. In other words, they're not going to be complex commands. They're going to be, what does it mean, a complex command? Like every computer needs to be able to do A plus B equals C. But what about A plus B plus C equals D? You don't really need to do that. You can just do A plus B and then a couple times and you can get the same result. But a complex computer might have specialized commands like that. A plus B plus C. Okay, MIPS implementation are primarily used in embedded systems such as Mobileye. So MIPS is actually quite old, but it's still in use. It's starting to be replaced, but it's still a good way to learn. So we're going to keep learning it. It's starting to be replaced by another thing called RISC-V, I think it's called. RISC-V assembly. But we're not going to learn that. Anyway, MIPS is still in use. We will program, and then one of the things that's good about it is we have this we have a simulator. Now, if you think about it, if we're going to write on MIPS assembly, we need to have a MIPS chip, right? We're writing for a particular chip. We're not writing for a PC PC is a certain chip. We're writing for a MIPS chip, a different chip. We're not writing for the PC primarily because it's a CISC system. It's a complex system. It has many more commands. So to make it simple, we're going to learn a simpler set of commands. But we don't have that chip in front of us. Theoretically, we'd have to plug our computer into that chip to program it. We'd have to actually plug our keyboard into that. And that would be our chip. So what we're going to do instead is use something called a simulator. The simulator is called Mars. It's just, what?
Should we do it ourselves?
And you can download it yourself for free. I have, do I have? Yeah, actually, if you do a Google search for Nachum Danzig installing, Nachum Danzig Mars, you'll find an instructional video for how to download it. It's pretty easy to download. You just download it. But I'll show you also how to use it. But that's for the lab. Obviously, show you that. The book that we're using is called Computer Organization Designed by Patterson and Hennessy, if you want to buy the book. It's worthwhile. Actually, it is a very good book. So it's a classic book. It's not, okay. Okay, so now let's go into a little assembly command. Again, this is introductory. This is really for the lab, but it's good for you to see. Here is a command that I would do in C++. A equals B plus C, right? That's the command you're all familiar with. How would I do that in Mars or in assembly, in MIPS assembly? Add A, B, C. In other words, I just write the word add, and and A is understood to be the location of the sum. And then B and C are the things that I'm adding together. Subtract the same way. D equals A minus C, so DAC. Now, she was a mathematician. Actually, I'll explain something interesting. She was a mathematician, so she thought in this term. She came up with this order even before this language existed, right? That's the assembly that Amazing Grace Hopper came up with. She could have written it differently. She could have written it sub AED, right? Sub AED. Take A, subtract B, and put it in D. There's no necessity that this is the order to represent this. You understand what I'm saying? If I would come up with assembly, I might write, the way you write D equals A minus C is sub AED, and put this sub at the right side. She put it on the left side. It turns out that the men who created the assembly in machine language did it the other way around. In other words, they did it AED. And she decided that since she's a mathematician, and it makes whatever, she didn't like it writing it that way. She liked writing it the other way. So she switched it. So actually, when you convert this into machine language, you're gonna have to jump around. The order is gonna change, but it doesn't really matter. Okay. Now let's go on. Let's do a more complex command. Here is one line: F equals G plus H minus per quantity I plus J. So how are you going to do that? You're going to need, there's no parentheses in this language. So therefore, you're going to need to do it in stages. Yeah.
What's the extraneous code that you were talking about earlier with that when you translate from a high-level language to machine code will happen? What's that extraneous language? This doesn't look extraneous.
You don't see that here. Here's not extraneous. No. In more complicated programs. I can give you an example, but not yet.
Okay.
I will give you an example in my slides, actually. Yeah.
Do you have to declare variables beforehand, or you just?
No, in fact, well, right now I'm teaching you, like the Rambam in his introduction to the Moreh Nevuchim says, that when you begin to teach something, sometimes you teach it wrong, just to make it easier to understand, and then you later will correct it. So this is actually wrong. There's no such thing as G and H.
So really just process that there's steps to doing
We're just learning a simple concept here, which is that we're going to learn what these G's and H's are. They're not really G's and H's. Okay. There really are no such things. This T0 is the real thing, but this G and H is a fiction for the purpose of teaching. G plus H, so I have to do like this. Take G and H and put it into T0. T0 will be a variable called T0, temporary. T stands for temporary. So temporary variable 0. And I'm storing this value. And then take I and J and store it in temporary variable T1. Now, when I want to put f, assign f the value of subtraction of temporary variable 0 and temporary variable 1. So we got the same result with using basic commands. You see that we don't have complexity like we have in C++. One line translates into several lines of assembly. Okay. Variables. So unlike high-level language, MIPS has a finite set of variables, or really I might rewrite this and say it doesn't have any variables at all. Variables are actually high-speed registers. So you know what registers are. They're just names of registers. And there are only 32 of them. There are 32 registers. And those are all the variables you got. And you can say, no, okay. We'll explain. You can say, well, I need more. So we'll deal with that. Each register, there are 32 registers. And not only are there 32 registers, the length of them is 32 bits. That means 4 bytes. And 32 bits or 4 bytes is called a word. Got to remember that, what a word is. Very important. A word is the length of the register, the size of the register. So if the register is 30, so we can call it is 4 bytes, then remember, how big is a byte? 8 bits. Everybody has to remember that for the rest of their lives. If I wake you at 3 in the morning and ask you how big is a byte, you should say 8 bits. I don't want any mistakes about that. People get confused. Bits, bytes. A byte is 8 bits. So if it's 32 bits, divide 32 by 8, you get 4.
So each register has a word in it.
Each register has a word in it. If you have a 64-bit computer, then your word length is how big?
Still 4.
No, 8.
The word is not 4 bytes. Word is the length of your.
The word is is in bytes, the length of your register. 40. I'll say I jumped a couple steps there. I'll say it slowly. 64-bit computer. You know what that actually means? It means your registers are 64 bits, as opposed to the MIPS, which is only 32 bits. For 30 years, all computers were only 32 bits because that was considered enough. And it is. I mean, now they have 64 bits in it. It's huge. To get to 128 will be.
I think they had.
Yeah, I don't know anything about it. Maybe they do, but there's no need. I mean, 64 bits is huge, huge, huge. Maybe they have one. We're gonna. I mean, if you take operating systems with me. What? No, you didn't. But if you take operating systems with me, we'll discuss how big is 64 bits. It's very big. Anyway, a 64-bit computer has 64 divided by 8 is 8. So that means it's 8 bytes in a register. So that means it's an 8-byte word length. But forget about that.
Oh, 8 a 32-bit long.
But this is a 32-bit long computer. So therefore, it's only got 4 bytes in a word. A word is not a fixed size. A word depends on the architecture. The word length is the size of the registers in that architecture. Yes.
The registers only like store numbers,
For sure.
but like not like characters or.
Well, have you heard of ASCII? What is ASCII?
ASCII is it converts to numbers.
Right. So in C++, when you write char, my char equals, or car, I guess you usually call it care actually. Care, is that how you call it? Care, my care. You call it char. And in Israel, they call it char.
Oh, that's
In
why.
America, they call it care. Because it's
Why would
character.
we say it's hard? Like.
Anyway, because they know that in America, CH is ch. That they know. Anyway, if I make a care of A, my care equals A, what's really going on? What's really going on is I made a variable and I stored it with the value 65. Because that's capital A or 97 is capital little a. I'm only storing numbers. Computers only store numbers. Everything is a number. In this language, well, we'll see. You can store letters, but in the end, they're stored as numbers. Everything is stored as numbers. So a 32-bit word length is enough to store the number 97, and therefore I can store A in it. In fact, 1 byte ASCII is designed to fit into a byte, so that I can actually store 4 letters in a word. Each byte can be a letter, unless there's something called Unicode, which is 16-bit or two byte letters, and that Unicode is a new thing, not ASCII, and it allows you to have like Hebrew letters, for example. ASCII is not big enough to have all the letters of all the alphabets. Good question.
Yeah, I'm still confused about what a word is.
A word is the size of the register. What in bytes? That's all it is.
So for 32 bits, every word is how many bits?
No, a word is 4 bytes. A word is 32 bits.
A word is 32 bits.
A word is 32 bits. The word length of this machine is 32 bits. That's the word length.
So there's only one word per computer?
No, 1 word per register.
1 word per register.
There's 32 registers. Each register has 32 bits or 1 word in it. 1 word of data. A word is a size. A word is a size, but it's a variable size. I don't know if you learned this in C++, but int, some people don't like you to use the int ever in your programming, because int is actually not defined in its length. It's defined to be the length of the word of that architecture. So on a 64-bit, a word is 64 bits, and on a 32-bit, it's 32 bits. At least that's the way. Yeah, that's the way it is, really. So therefore, we have short and long. Short means I want 32 bits, and long means I want 64 bits.
So there's in.
So I'm just saying, an int is actually defined as a word. So it changes depending on the architecture. And in the MIPS architecture, the word is 4 bytes. Yeah.
So there's 4 bytes in each register.
There's 4 bytes in each register. That's another way of saying
And
it.
there's 32 registers.
And there's 32 registers.
So
Yes.
therefore you can have very, very long word. I mean, very, very long
Very.
command.
No, what we're going to learn, every command is also 32 bits long.
So in the end, you can have a very long.
Let's not go too far ahead of ourselves, because we didn't learn enough to. You don't have enough. You don't have. We're still painting the left-hand corner of the picture. We didn't get the whole picture. So there are 32 registers. That means theoretically I could store 32 variables. That doesn't seem like very much if I want to write a very big program, but yet I can write a very big program. Why? First of all, why do we have so few? Because registers are hardwired, right? They're physical things. If I would have more than 32, the computer would start getting larger, and larger means slower. Why does larger mean slower? Because the electricity has to travel further distance. And even though it's traveling at the speed of light, the more distance it travels, the slower it goes. So we'd rather have fewer registers to make our computer faster. But we'd rather have more registers because it's nice to have more registers. So we have to find a balance. So 32 is a good balance. Each register can be referred to by its number 0 through 31. So we can talk about register 0, register 1, etc. Now this is this other idea. Every command, like add ABC, when it's translated into ones and zeros, like we said it is, how many ones and zeros is it? So the answer is every command is exactly 32 ones and zeros. And there, a command itself, in addition to variables needing to be stored in the computer, the commands need to be stored in the computer. Your program is sitting in the computer's memory, and it takes up bytes of memory. How many bytes? So every command, every add ABC is 32 ones and zeros, 32 bits. Question. I leave this as a single slide because it's an important concept. And there's nothing to say. That's it. You just have to know that. Okay, not much details I need to say about that, but every command is 32 bits. Okay, let's go back to our example. Now we're using registers to translate. Let's go back to that same command, and we're going to use registers because actually there are no G, H, I, and J. Like I said, that's a fiction. So if we want to translate this, we have to say, let's assume that the variable, that the values are, that the value that G has is actually stored in register S0. Remember I said that every register has a number, 0 through 31. They also have letter names. Just they've given multiple, like everybody has a Hebrew name and an English name. So these have a number name and a letter name. And the letter names are, we're going to see their S's and their T's. For right now, just know that they're S's and their T's.
Is there a difference between S0 and T0?
Yeah. S0, T0 is 8, and S0 I think is like 16 or something. Yeah, it's a different register.
We only have 32 registers.
Yes, 16 is yeah. So S goes up to like 8. There's S0 through 8. There's T0 through 8.
So that takes care of 16.
That takes care of 16, and then there's 16 more. So the S's and the T's we're talking about. Why are they called S's and T's? S means save, variables that we'll learn about that later, but actually Avi will teach you about that later. But the S's are for variables that are meant to be saved, and T's are temporary, not to be saved. So let's assume that the value that I had in G is in S0, the value I had in H is S1, the value I had in I is S2, and the value I had in J is in S3. Then the command would look like this. Take S0 and S1 and put it in T0. Take S2, S3, put it in T1. And then take the subtraction of the two and put it in S4. So that's like the same example we saw before, but written with register names the way it could actually be written in language. Yeah, I overlooked that. As a dollar sign, the custom is to write a dollar sign. In fact, you have to write a dollar sign. In fact, in C++, if you know the rules of the variable definition, what are valid names? You can't start a variable called like plus symbol A. But you could start a variable $A. The reason why is because because they wanted to support programmers who are used to writing dollars in front of their variables. Because in assembly, you always write a dollar in front of your
Dollar for every variable?
every variable. Well, we call it a variable. It's a register, but it's a variable or a register. You view it in two different ways. In hardware, it's a register. Conceptually, it's a variable. In your conception of how you think about programming, it's a variable.
The dollar signs are only for registers or for?
Yeah, but all you have is registers. There's no variables. So you're gonna always see
The
dollars.
first problem they just
The
weren't
first
there.
problem that I gave was wrong. I
Oh,
couldn't
okay.
do that. That was what I was saying. This is the corrected version of that first problem. Okay, how do we store more variables than 32? Where do we keep static array data? Let's say I want to make an array that has a string in it that says like, Wednesdays are my favorite days because my parents give me hot dogs. That's your sentence. And that's much more than 32 letters. How you can't store that each letter in given register would be crazy. But if you have a much longer sentence. So we have to have arrays. So we have something called a data segment. More on this later. I'm just warning you, there's something called a data segment. Data segment, yeah. Okay. Basically, data segment, what we're going to have is a pointer to an area of data. Assuming data is in the data segment, we want to load it into one of our registers. Essentially, we copy data from memory to the register. So now we're teaching a new concept. It's something called memory. Memory is when you buy a computer, you get, 16 gigabytes of memory. Nobody talks about how many registers there are. There are registers. You have 60 registers, whatever. You have a bunch of registers, but you also have gigabytes of memory. Memory is huge. So we copy data from memory into registers bit by bit, or not bit by bit, byte by byte, or actually not byte by byte, word by word. We're going to copy words of data into registers. Then let's say I want to print out Wednesdays are my favorite day. So what do? I'll copy the W into a register, then print it. Then I'll copy the E from Wednesday
into a register and print it. And I'll copy the D from,
Where am I getting?
and I have a pointer to this data. I have a pointer, I have an address. I have an address of where in memory that sentence is being stored. When I want to print it, I'll grab each letter one by one in a loop and I'll print it out. So I have access to that memory because I have its address. And when I want to print it, I'm going to have to load the letters into registers so that I can then print it. I can't do anything on any data unless the data is in a register. I need to put it into a register. Question?
Yeah, so from the data segment, it puts it into memory, and then once it's in memory, we can access it whenever we want using its address.
No, data segment is memory.
Data segment
Your
is-
word, yeah. Data segment is the memory. So once it's in memory, I can copy it into registers.
But it's there, like it stays there even
It
though.
sits in the memory as long as the computer is on.
Okay.
Memory is not the disk. Yeah.
Would this be, for example, like in C++ we're reading about files and copying files?
It's not the same. No, that would be from a disk. Files would be a disk. This is from memory. You never did this in C++. You just said, declare an array, and here's the contents of the array, and you just did that. And now we're going to say, wait a second. There's a difference between data stored in an array and data stored in a register. Okay. So we are going to want to copy this data into a register. We need to do something called loading. Like you load onto a bus or onto a truck the stolen television sets. So you load them onto the back of the truck. Where you need to specify where the data is. What does that mean? The address. You need to know the address of the data. You need to specify where to copy it to, which register. If you want to put it into register 0, register T1, T2, S1, S2, where do you want to put it? You need to specify how many bytes to copy. Do I want to copy an entire word, or maybe a half a word, or maybe just one byte? So we're going to see that that's all in the following command. So let's say, for example, so here's my load word. LW stands for load word. That's exactly what I was talking about. Now, for example, I have this command in C++. G equals H plus my array. 8. What is that? That is actually a very complicated command. Because if you think about it, what am I doing there? I'm saying jump over to memory and an address called my array. And then go 8 spaces from there. That's what the 8 means, right? I don't know if you ever understood that. In C++, when you say 8, why does an array start at 0 in C++? Because it's say, go to the beginning and then don't move. 0, go 0 forward. So when we say 8, we mean go 8 forward. So it's the 9th place. So go to my array, go to the 9th place, grab that data, bring it into a register, then take the value in register H and put it into G. So in order to do that, we have to so in C++, in the MIPS, we have to do like this. Load word, and the 8, this is really confusing, the 8 goes on the other side of the parentheses. And the S3 is actually the address, assuming, this program is not a complete program. It's just assuming that S3 is the address of the array. Somehow, we're not going to explain right now how, but somehow S3 is a pointer to the beginning of the array. It knows where that array is. So then I say, go to the 8th location starting at S3, grab that data and store it in temporary variable 0. Then take temporary variable 0 and add it to S2, which we're assuming is our H. And then put it into S1, which we're assuming is our G. So you see that I have to do these 2 steps.
What if the memory is not in register? It's in the memory.
Say that sentence.
No, let's say the my array.
Yeah.
Let's say that's in your memory.
It has to be in memory.
So here it's assuming that it's in a register.
No. I'm assuming that the address of it, the location of it, because memory has lots of addresses, and every single byte has an address. So I need to know where it is. So somehow I got the address of it. In other words, I like to give a mashal. If you want like the mashal. in a hospital, you have a lot of beds, a lot of people sleeping there. And then you have a few surgery rooms, maybe only 8 surgery rooms. When you want to do something to one of the patients, what do you have to do? You have to go to his sleeping room and put him on a gurney and wheel him to the surgery room. Then do whatever you want to do, take out his appendix, and then wheel him back to his room. Why do they do it that way? Why don't they just, in every room, build electric lights for surgery and oxygen tanks and have everything in every bedroom? It would be a waste of space and a waste of money. It would be very expensive. Every room to be fully equipped. So what you do is you have lots of space for people to sleep, but a few places for actually having all the equipment and doing all the work. So you need to move people in and out all the time of the surgery room. The surgery room ideally is constantly got somebody in it, and you're moving them in and out as you finish. So the surgery room is like the registers. You have 32 surgery rooms, places where you can do stuff to numbers. You can't do anything in memory. When it's in the bedroom, it can just sleep. Now I need to wheel them into the surgery room. So that's my load word. And I have an opposite command is store word. Put him back into his bedroom. So I got my load word and my store word to wheel the variables back and forth into registers. Once they're in registers, then the CPU, the CPU is central processing unit. Then the actual mind of the computer, the brain of the computer, can actually do stuff like add or subtract. The CPU cannot work directly on numbers in the bedrooms, in the sleeping rooms. They have to be in registers. They can't be in memory. And just like in a hospital, there's a lot of sleeping rooms. In the computer, there's a lot of memory. But there's a finite amount of registers. Yeah, question?
Just like, I guess, clarification.
Just like what?
Clarification for the first command that you're having with the load word. So you're loading into T0, you're going to the memory location that's in S3, and you're going 8 bits from that, like the next 8 bits.
I'm jumping ahead and I'm grabbing, no, it's 8 stands for.
Yeah, I'm just confused about the 8 essentially. Like,
Well, actually, this is also a fiction here. We're going to correct that in a minute. The 8 here, if this slide makes any sense, then what it means is 8 words forward.
Okay, so that's basic. So it would go, so we're going to T0, we're saying that's what it's going to be like our storage right now, our surgery, for example. And we're going to go to the memory location that's stored in S3 and take the next 8 words from there.
No, not take all, I can only take one word.
So
But jump
8
ahead
words and take the
And take,
8
it's like if I have Wednesday is, so the 8th word might be the Y of Wednesday.
So I'm going to take the 8th word from that location.
From that location. It's how much to jump forward.
Thank you.
I think at a certain point I'm going to stop with these slides because getting too much into the lab. But it's good for you to see a little bit. So here we go. Each byte has an address. Therefore, all right, I'll explain something interesting here. If the command is load word, then it means grab an entire word. Grab 4 bytes, right? A word is 4 bytes. That's what load word means, load a word. There actually is a command called load byte, LB, which means grab just 1 byte. Depends on what I want to do. If my letters are in bytes, then load byte could be good. If it's numbers, then they're probably in words, right? Usually integers are 4 bytes long, whereas characters are 1 byte long. So if I want to get what's in a particular byte, for a letter, then I'm going to use load byte. If I'm going to want a number, I'm probably going to use a load word. I could have my numbers stored in bytes also. So I have load byte and load word. But this number here, 8. Okay, sorry, before I say that, go back. When I'm doing a load byte, I can give any address I want, any byte I want. But when I do, because I can load any byte of the memory. But when I do a load word, I must give it an address which is a multiple of 4. 0, 4, 8, 12, 16, 20, 24. Must be a multiple, and then we call that a word boundary. So I'll draw that for you. For example, well, this is a bad pen, but let's say I bite, 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 bite. And let's say this is 0. This is 1, 2, 3, 4, 5, 6, 7, etc. These are bytes, not bits, bytes. So I could say grab these 4 bytes from 0. What I cannot do is say grab these 4 bytes from 1 to 5. I have to be on what's called a word boundary. I have to or grab from 0, either grab from 0, grab 1, 2, 0. Did I draw these numbers right? 1, 2, 3. I can do 0, 1, 2, and 3. Or I can do byte 4 like this. I can only grab either this word or this word. I can't grab some kind of Frankenstein word in the middle, because I can't grab some from here and some from there. It'll give, if you try doing it, and I've seen students in the lab do this, and then they give this weird, they give an error. The compiler won't let you, and you'll want to understand the meaning of it. But it'll say something like invalid word boundary, right? You have to be at a word boundary at 0, 4, 8, 12.
And then with 64 bits, it would be from 0 to 8.
Yes, it would be a 64-bit machine, and yeah, the word boundary would be different. So load word, but load byte doesn't have that problem, because load byte says any byte. It's a byte. It has to be on a byte boundary. Whatever you address is a byte boundary. But it comes out that there's an address here, an address for every single thing. So if you put that together, all right, wait a second. Wait, before let me go on. So actually, to do this command, let's read. Now let's do it a little bit more correctly. Look what did I change? Anyone see the change? Right, it's 32 instead of 8. This is more correct. This is correct. Why is this correct? Because actually, this number is it doesn't know to jump by 4s. It's the actual number to go. So if I say 32, what I mean to say is 32 bytes forward, which is 8 words forward. As I can't tell it, I mean, it could have been simply whatever. It's very low level. So it would let me write theoretically 3, the number 3 here, and then it would give me an invalid word boundary problem, right? If I wrote 3. In other words, I have to write here, if I'm doing a load word, this number here must be a multiple of 4.
What is 32 telling? What if I wrote 8?
32 is telling me go 32 addresses forward, which by a fact is 8 words forward, which is what I wanted to do. When I did this over here, the following example is not fully correct. I did this, I wrote 8 over here, because that's the way we think in C++. We think, oh, I want the 8th word, I'll just write 8. But actually, you can't just write 8. You got to write 32.
Are you talking about each is an
Because
array of
each-
strings, or what if it's just an array of numbers?
No, we're talking about an array of numbers. We're talking about an array of numbers, but we're talking about an array of words.
Each number
In C++, we think about strings and word and ints and
is
characters. In this class, we're going to think about words and bytes. There's no such thing as an int. There's no such thing as a character. It's just, do you want a byte? What would you like? You want a byte? 2 bytes? 4 bytes? You know, and then from where would you like it? So it's just going to take this number and add it. It's just going to put it in the full adder, and it's going to take whatever number is in S3 and whatever number is 8, push them together and give you a new address. So I better write the right number here. I can't just, it's not going to magically know that when I say 8, I mean 8 words. It's going to think I mean 8 bytes. So since it thinks I mean 8 bytes, since it thinks that I mean 8 bytes, and I don't mean 8 bytes, because I said over here 8, that means 8 words I wanted. In C++, this would mean 8 words ahead. Notice I didn't write any type in this example. You don't know if this is an array of integers or floats or what it is. I didn't write a type here, but I'm assuming that it's floats, let's say, or ints. So the correct way to do it is with 32. Here, what did I write here? The above C++ command, nothing better than just reading my file. the above C++ command intends to copy the 8th word from the array. So we need to jump 8 times 4, or 32 addresses in the array to get the intended word.
So if we want to go to 7 and 28,
Yes,
It's 32. When you say 32 addresses, you mean 32 bytes?
yes. Because every address, every byte has its own address.
Bit byte has not bit
Byte. Yes, byte. Every 8 bits has its address.
and every 4 bytes is 1 word.
And every 4 bytes is 1 word. So if I want to go to the next word, I got to go 4 bytes ahead.
You can only grab 5 words. You can't grab.
You can only grab by word. Well, we said there's a load word here. This is called load word, which means I'm intending to grab a whole word. There could be a load byte command. There is a load byte
how
command.
many bits are in each byte?
8.
So it's 8 bits in one byte, 4 bytes in a word.
Yes. Remember that. 3 and 1. Here's a picture of the memory. It starts at, this is also important, x0. Who knows what x0 means? Sorry, 0x. What does 0x mean? No? It's an address. Usually addresses have that 0x in front of it. It's true. But why? It actually means something. It means that the number is in hexadecimal. You know what hexadecimal is? Base 16.
The X0, X tells you it's
Yeah, if you see a number with x0 in front of it, it's in hexadecimal.
wait, X0 or 0X?
Sorry, 0. What I wrote over here.
Okay.
0x. 0x means it's in hexadecimal. So this number is 10 million, right? But it's actually, is it 10 million or 10,000? Hard to count the zeros. Yeah, 10 million. That's 10 million. But it's not 10 million. It's 10 million hex. So it's a lot more. Right? It's in base 16. It's a lot more. That's why, by the way, you notice if you have 0x, a lot of times you'll have letters. Because what's after 9 comes A until F. F is the last number. So 7 F, whatever, is like writing, 7999. It's like writing, so F is the highest number you have, highest digit you have. This is showing me the memory. It basically starts at 0x0 until 0x7ff. This is 4 gigabytes of memory. This is 4 gigabytes. That's how much memory can be addressed by 32 bits. I don't know if you understand that concept. It's something called an address space. The address space, if my addresses are all 32 bits, then there's a limit to how many addresses I can have. It's like if a 2.zahut number has got 9 digits in Israel, then there's a finite limit of how many, they can't give a 2.zahut to everybody in the world, because there's 7 billion people in the world. There aren't enough numbers in 9 digits to address every single person. But there are enough to address every single Israeli. And then some. Not that much, actually. I'm always perplexed by how close it is. It's like 20 million. How much is it? 9 digits is how much? Oh, actually, there's something. Because one of the bits is picoret. One of the bits is extra. So it's actually really only 8 bits. So 8 bits is 100 million. 99 million. 100 million. I guess actually. We're a long ways away from that. But still. Because all the people that die and all the people that are born, we'll get there. We'll get there. When you guys have grandchildren, you probably have a new digit. So anyway, the number of numbers in 32 bits, if I have to give every byte a different address, then I'm limited by how much memory I can have if I have a 32-bit address. Whatever I can address by 32 bits happens to be 4 gigabytes. So if you want to have a 16 gigabyte computer, you need to have a 64-bit, or at least a larger than 32-bit address space. So we call it an address space, because it's the space that can be addressed by those number of digits. The 32-bit address space can address a space the size of 4 gigabytes. We'll get into some of this math.
So the address space is just like the amount of addresses that can be held in that space.
The amount of addresses that can be held in that number of bits. In other words, in that number of address bits. It's like if I have only 2 digits, think about something like this. If I have a rule, I'm the mayor of Nachumsville, and I make a rule that no house can have a number higher than 99. I don't want any houses. I don't want houses with like 1,000 Main Street. I want the highest number is 99. So then, how many houses can I have? Let's say like this. I want a 2-digit address for every house in my town. It can be 01, it can be 12, it can be 24, it can be maximum 99. So how many houses can there be on a street before I have to change the name of the street? 99, 100, 0 to 99, 100. So the address space in my town is 100 houses. That's the address space. Because I have 2 digits. I have a 2-digit address space. 2-digit, or say it like that. A 2-digit address space yields me 100 possible houses. That's in base 10. But if I'm in base 2, how would a 2-digit, if I limited my addresses to 2 digits and I was in base 2, how many houses could I have on the street? 4. 0, 0, 0, 1, 1, 0, and 1, 1. Right? We've got 4. So we're in binary here. So a 32-digit address limits me to 2 to the power of 32 addresses. With 2 to the power of 32, well, it's 4 gigabytes. How do you know that? You can do that very quickly. You guys have to know another thing, extremely important, write it all down. Write this down. 1 kilobyte is 2 to the 10. 1 megabyte is 2 to the 20th. And 1 gigabyte is 2 to the 30th. And what do you think 1 terabyte is? 2 to the 40th. So 2 to the 30th is 1 gigabyte. That's what I just said.
2 to the what?
So what is 2 to the 32? Well, it's simply 1 gigabyte times 2 to the 2. 2 to the 2 is 4. 4 gigabytes. See, you can do the math in your head. You see what I'm saying? 30, if 30, I just said 2 to the 30th is 2 to the 30th is 1 gigabyte. And 2 to the 32, well, I can just separate the 30 and the 2 and look at the 2. It's 2 to the 2. 2 to the 2 is 4. So it's 4 gigabytes. So if I have 32 addresses, if I have 2 to the 32 addresses, I can at most reference 4 gigabyte bytes. That's it. I can't put more memory in than that. I would have no address for it. I wouldn't be able to address it. Question?
I'm a little confused by the 2 to the 10th what?
Well, what is 2 to the 10th? Type it in your calculator. 2 to the 10th is 1,024.
Right.
We call that a kilobyte.
That's
A kilobyte. Oh, well, when we're referring to 2 to the, you're right. You're asking a really good question. Well, what? 2 to the 10th bytes is a kilobyte. I really should say it like that. 2 to the 10th bytes is a kilobyte. 2 to the 20th bytes is, but by the way, there's a little fiction there going on because when you think of a kilobyte, you think 1,000 bytes, right? But it's not 1,000 bytes. The kilobyte is not 1,000 bytes. It's 1,024 bytes. And when you think of a megabyte, you think of 1,000,000 bytes, but it's not. It's 1,000. I don't know what it is. It's 1,024 times 1,024, which is obviously more than 1,000,000. Well, it's 1,000,000 and 100. 1,000,000 and then 10,000. So that's why when you buy a disk and it says on it that it's a gigabyte, and you put it into your computer and you look at it and it says it's not a gigabyte. It says it's less than a gigabyte. You know why? Because the Ganavim who sold you that thing, they told you it was a gigabyte, but what they really meant was it's a billion bytes, exactly a billion bytes, and not a billion etc. bytes, which is what it should have been. But when your computer looks at it, from the computer's perspective, it's not a gigabyte. because a gigabyte is a million, etc. Million plus or more. But they didn't tell you that. They told you exactly a million. So when you see an advertisement that says it's a million gigabyte, what they mean is the lesser number. They mean
my
that.
phone is 32 gig. It's really 31 point whatever.
Yes.
That makes sense. If you look at your storage, you'll realize your storage.
Yeah. Everyone thinks, oh, it's the operating system. That's something else. It's the plus.
And wait, that
They're they're cheating. It's just that universal
the reason for
cheating.
that is why, because there's how does that work mathematically? It's really
How does it work?
yeah. I mean, how does that work mathematically? That it becomes 31 point whatever instead of 32.
Yeah, exactly.
Why?
Because if they would really give you, because what they're saying is like this, there's two numbers. There's a million bytes, which is a million bytes. And then there's a gigabyte, which is a million and whatever bytes.
It's close to the amount.
It's close. It's close to a million. That's why they call it that.
But they're
But when the salesman sells you the thing, he sells you, yeah, I'm giving you, it's like, but he gives you, it's like you buy a brand new apartment in Israel. They tell you how many meters it is. But the meters is the gross meters, which means they count the walls. They count the thickness of the wall. It's counted. They count the thickness of the wall. So you get 100 meters and you go in and measure it with whatever technological tools you have to measure it, and you'll turn out that it's not 100 meters. It's going to be 90 meters because they counted them. So the same thing, in other words, the salesman is going to tell you it's 100 meters. He's not going to. Why would he give you if he has a choice of giving you two numbers, he'll give you the number that makes him look better. So when they make a disk, they actually do a bizarre thing. Every company that makes disks and makes memory, they make it when they call it 100 megabytes, what they're really giving you is 98 megabytes. And then, but they call it 100. They call it 100 megabytes because it's what it is 100,000 bytes or 100 million bytes. 100 million.
Like that's 2 to the.
Instead of 2 to the exactly, they're giving you it. But in computers, in base 2, we call 1,024 1,000, which is kind of weird. And they say, well, we're salesmen. We call 1,000 1,000. In this class we call 1,024 1,000 called a kilobyte. Kilos from the Latin meaning thousand, right? Mille is million. Okay. So anyway, this is the memory you see here that why am I showing this? Is something called the text segment, the data segment. And the data segment is essentially all of this up until here. Well, it could all the way go all the way to there, but whatever. Just I want you to know for now the data segment and the text segment. The text segment is where your actual program sits. In order to run your program, it has to sit in memory. The program doesn't sit in the air. It doesn't sit on a disk. It sits in memory. In that 4 gigabytes of memory. When let's say it's on a disk, you've got to copy it from the disk into memory before you can run it. That's the text segment, and then this data segment. Okay, a data segment is where you store your arrays.
What is function call command or whatever was it there?
What is what?
Function call data up at the top.
Forget about that for now. Okay, let's skip that. Here you see the store word command. There's a load word. That's the wheeling the guy from the bed into the surgery room. And the store word is going the other direction. Notice the weird thing about it is that instead of what you would be used to in C++, what you do is you just change the order of the variables. Here we change the name, but we leave the variables the same. This means take this address and go 32 forward and copy it into T0. This means take T0 and copy it into this address. The arrow is pointing to the right. Here the arrow is pointing to the left. How do I know? Because how do I know the difference? Because one is called load word, one is called store word. You understand? A little bit weird.
Out file and file.
It's what?
The out file and in file.
Yeah, we have a special command that tells me which direction to go. This means go from T0 to here, This means LW means go from here to T0.
So SW go from T0 to 48.
Yes. It just goes the opposite of low root. Here I'm just showing you that you can do I equals I plus 1 or I equals I plus 4. Notice that I can use the same register twice, right? Okay. Ah, here we go. Now, let's talk about representing in MIPS instruction format. Remember I said that every command is 32 bits long, and I also said that I was going to show you how that's true. So let's see if that's true. So so here's a command: add T0 S1 S2. You're familiar with that command by now. So I need a way of representing add. I need a way of representing T0, S0, and S1. So T0, oh, I'd like to show you, wait a second, let me show you. Let me show you. Yeah, look at this picture. You see this picture? Can you see that? It's too small. Oh, I visited with also open picture. Can you make it bigger? Here. So look here. T0, let's understand this little table here. T0 is also called 8, register 8. But you know why it's called register 8? Because that's its actual value. That's its address. The way I refer to it is by the number 8. So when it says T0 to T7, it means go up. So that means T1 would be 9, T2 would be 10, all the way up till T7 would be 15. And S0 would be 16. And I guess right. I said to you before that. I guess I remembered right. S0 is 16, S1 is 17, all the way up to S7. Now, there's a really weird thing here because look at this. T8 and T9 are after the S's. It's really weird, right? I don't know why they did that, but you would think that T8 would be 16, but it ain't. T8 is 24, and T9 is 25, and that's it. Now there's 8 S's and 8 T's, but then there's 2 more T's. So there's actually 10 T's. And then they did it this way. There's also some A's over here, but you see they all have a number. So as I can refer to T0 as 8, I can also T8 I can refer to as 24. Okay, that's what I want to show you because that's going to be important. You're going to on the exam you'll get a table like this. So you won't have to memorize this, but for now let's remember it. So look, S1. Wait, according to that table, what's S1? 17, right? So S1 is 17. So that's why I wrote a 17 over here. Everyone sees that? S2 is 18. T0 is 8, right? That's from the table. What about all the other numbers here? Well, this is unused, so that's just 0. And this is, in order to indicate that this is an add command, I have to do 2 things. I have to write a 0 over here and a 32 over here. Together, that means it's an add. Because if there's a 0 over here and some other number over here, it could be subtract.
Why 32?
Oh, because we have a table for that too. Let me find that table.
Like ASCII or something?
It's like ASCII, but for commands here. If I go, let's say, MIPS instruction opcodes. Here. I don't know. This is good. Yeah. Yeah, here. No, I don't like this one. Let's do green card. Green card. And we're 2-0.
Will we get this on the
You get this on the exam. All right, look at the ad over here. See what this is? So this is, what is this? This is a table. You guys are with me? Yeah. This is a table of commands and their numerical equivalent values. Right? Remember we said that Grace Hopper, she met all these men and they were writing in numbers. And she came up with this table. She said, let's, instead of numbers, let's write words. So now we're going backwards and we're going from the words to the numbers. So add is actually 0 in the left-hand box, 0/20. Okay, so what did I write? I wrote 0, but I wrote 32. Why didn't I write 20? Let's go back.
Is what's 32?
What?
What's 32?
What?
Yeah, what's 32?
32. It's 32.
The 20 is that. You're adding small.
No, but I want to do add, and according to this table, add is 20.
Well, if it's in hexadecimal.
So what's written over here? What's written over here? HEX. What does that mean?
Hexadecimal.
Right. What's 20 in hexadecimal? 32. Right? 20 is 16. Base 16 is 16 and 16. 2 16s. That's 32. So if I want to be between using these two tables that I just showed you, I can take this command and say that add must be 0, 32 plus these numbers here. Now look, notice that the order, remember I told you the order switches? Remember I said that Grace Hopper switched the order? So look here, S1, S2, and then comes the T0. The order switches around. Now wait a second. Now
What is this?
what are
It's that be adding 17 to 18 and putting it into
this is the translation of this command.
Yeah.
Adding S1 and S2 and putting it into T0.
we haven't. So what is this like, little chart practically?
This is well, we're the first stage of translating this into machine language.
Okay.
We're translating from assembly into machine language.
And what is unused?
It's just unused. Well, what are these? Well, what you're really asking is what are these different fields? And I'm gonna the next slide. I'm gonna show you.
Which languages are we translating from?
Assembly into machine. So actually, these fields fit into 32 bits. And here I drew it just with lines, and I didn't say how many bits this is and how many bits this is. Now I'm going to give them names. In other words, we're not just going to call this the first one, the second one, the third one. We're going to give them names. And we're also going to give them sizes. So here's what I do. The first one is called the opcode, otherwise known as the operation code. In other words, what code is it? What am I doing? Am I adding? Am I subtracting? Am I load wording or store wording? What am I doing? But actually, so that's the opcode. Then the next section, and that's 6 bits long. I got 6 bits for that.
And that's like that's given.
What?
Like how do you know the operations?
I'm telling you.
Oh.
It's always 6 bits.
Okay.
It's always 6 bits.
It's always 6 bits.
It's always 6 bits.
Oh, okay.
These are fixed. Well, there's actually going to learn 3 different formats. This is called a format. This is called the R format. If you look over here, this is the I format. It's different, but it also has 6 bits. That's the opcode. And there's also a J format. There's a J. Here's a J format. Also, the opcode is 6 bits. The one thing that's always the same between all, there are 3 formats. Always the opcode is 6. And that's basically, you need that to be, because it needs to start off. Basically, if it's a 0 over here, I'll tell you even more. If it's a 0 over here, then it means that it's an R type. In other words, all R types, the opcode is 0. If it's an I format, then the opcode will be something else. Okay, so the computer, when it reads the opcode, immediately knows that it's an R type format. And then it knows what to do with the rest of the numbers. That's very useful. Because it knows how to interpret the rest of the numbers now. It read it, it said it's a 0, it immediately knows that what the other fields are. The left-hand box is called the opcode box. And that, if it's 0, is an R type.
What is an R?
Well, we're gonna see. R type for now is just there are 3 types of commands. Just R, for now, we're just gonna call it R, I, and J.
So that's
Rabbi Yisrael Yaakov.
when you say 0,
Or Rabbi Yaakov Yisrael.
so that chart.
Is R, do you know RJJ is?
Yeah, that's right. We're from Edison.
You're from Edison?
Yeah.
Who is RJJ? Rabbi Jacob Yaakov, what is his name?
Jacob Joseph.
Jacob Joseph, yeah. Yeah, Rabbi Jacob Joseph. Who was he?
Really famous.
He was like the he was like the first gadol from Europe who came to New York. No, not Rabbi Herman. What? No, it's Rabbi. No, that's his name. Rabbi.
Oh, Joseph is his last name.
Yeah.
Oh, that's
Yeah.
what oh.
I just know.
I definitely read it.
It's
Definitely in a biography that I read.
Yeah, he was this gadol from Europe that came in like, I don't know, the 1910 or something like that, to try to create Yiddishkeit in America. And the main thing he tried to do was straight kashrus. There was no kashrus certification. And he pretty much failed in everything he tried to do. And he died miserably. Like he died and he had a terrible, it didn't, I mean, I don't say he died miserably that he suffered, but he died and he didn't really succeed at anything he tried to do. And it was only later that kashrus really started in America. And there's a terrible story about his wife, because when he died, everybody, all the cemeteries wanted him to be buried in their plots, because they could charge more for people to be buried near him. And so they offered his widow money to bury in their plot. And different people are different sums. One cemetery offered her like in perpetuity, a certain amount of money every month. She said, well, that's the best deal, because then I'll always have money. I'll always be able to live. So she went with that one. And then like a year later, they stopped paying. So, but the interesting thing it's connected to my family, because my great-grandfather is a horrible story. It's a horrible story. See, you always hear good stories. I told you that. The interesting thing is that my great-grandfather, actually made a lot of money in New York. He ended up losing a lot in the Great Depression, but he is buried, right? He is buried like 10 feet from Rabbi Jacob Joseph.
Where?
It's in Queens. He's buried in Queens. It's a cemetery there.
Everyone knows this, then they all just go back to the cemetery and say.
Oh, there's another story. There's another story about this. Not a bad story. This is not a bad story. This is not a bad story. But in the newspapers, they wrote, it was like, I read an article, there was like a huge procession of Jews walking down the street for his funeral, for his levaya. All the streets in the Lower East Side was all crowded. And they were walking by a factory where Goyim were working, and the Goyim started throwing things out the window at this crowd. And so the Jews went upstairs and started beating up also the women, like the old women they all went upstairs and started beating up the Goyim. And actually the police were called in, and then the police came and beat up the Jews.
Oh, okay. So that's fine. So when did you go to
So that was at the funeral of Rabbi. Just to give you an idea of what was going on in New York and why he didn't succeed. He had a hard time succeeding. It was a hard time.
Oh my gosh.
This is the stories of Jacob
Wait,
Joseph.
why didn't she get the money in the end? Why did people just go back to the funeral if it was so
And
well known?
beat them up. I mean, nobody going, no, a year later, like everybody forgot about it. He's there. What are they gonna do? Dig him up? Put him somewhere else?
So,
It's pretty wrong. But it's a good lesson. Take the money now.
Wait, is that the lesson to learn, or maybe that just because they ask they offer the highest amount, it's not going to continue. So maybe like some of the other people would have like continued. So like
maybe we should marry someone.
less
who-
money.
No, the other people were gonna give a lump sum. And
Oh.
one place said they wouldn't give a lump sum, they'll give her in perpetuity money. And she went with the perpetuity. And I'm saying,
And
well,
then
listen,
what happened? Then they buried someone there anyway.
well, he was already buried.
Oh, he was already buried.
A year later, what? They just stopped paying. Go sue them. Like, what's she gonna do? What's this old lady gonna do? It's pretty bad. Bad story. But that's a true story. I read this, yeah, anyway. I read this because of those things.
Wait, so then why do your like relatives want to be buried in the future like that cemetery? Seems to be like.
I assume, knowing my great grandfather as I don't, but he bought the plot, way before he died. So maybe he bought it at the same time, just after he got buried. My great grandfather came to America when he was 13 from Europe, from Russia. And as the only member of his family, came out alone to make money. And he always, being from in America was not really possible at that time. He came in like 1880. And, but he went to yeshiva, he went to cheder. So his whole life, he kind of was like dreaming of the shtetl, dreaming of like he married a woman who came from a good family. So he probably wanted to be buried next to this guy. He's trying to like recapture some Yiddishkeit. So he bought that cemetery. I don't know when he bought it. He bought that plot. But interestingly, his wife is not buried. She was a gypsy. His wife died a lot earlier. Anyway, okay, so where are we? So we're at the so anyway, RJI, Rabbi Israel Joseph. So Jacob is Yosef. So R is the basic type. It means R actually stands for register type. And why is called register type? Because there are 3 registers here. And we call them register S, T, and register D. They stand for register source, register. Well, this is also called, what is it also called? I called it register source again. RS is register source. RT is really register. In this case, it's the source, but it's target. The T stands for target, but it's confusing to call it target here because it's not really the target. Remember, it's the 2 S's that we're adding together in our add command. The target is really is the third one, which is the destination. So RD stands for registration. So these are the names that we give to these fields. And this is how many bits they are. Now, who is smart here and can tell me why it's 5 bits? It's a great question. Think about this. Why is it 5 bits? Why isn't it 4 or 6?
Because if it's not 5, then it won't add up to 52.
Something like that. Yeah, you're in the right direction.
2 to the 5th is 32.
Oh, 2 to the 5th is 32. 2 to the 5th is 32. If I have 5 bytes, five bits, what I can have 0, 0, 0, 0. The max I can have 1, 1, 1, 1, 1. What's 1, 1, 1, 1, 1? What?
31.
31. How many registers are there? 0 to 31. So I can have any possible register here. If I would only have 4 bits, then I wouldn't be able to put every possible register. If I would have 64 registers, then how many bits would I have to have here? 6, right? I'd have to have 6 because I want the flexibility to be able to put any register here. I don't want to say I can only put half the register. So this is 5 bits to be able to reference every possible register. Everyone got that? I mean, just because some people got it doesn't mean everybody got it. 2 to the 5th is 32. That means that I can have all 32 registers referenced by 5 bits. That's why I have 5 bits for each register. And we call which register? Instead of calling it the first, second, and third, we call it the source, the other source, and the destination. But the T is because sometimes we call it also the target.
So those 5 bits are like holding the name of the register?
Yes, the name or actually the number of the register. Like if it's registered, we saw that table. If it's register 8, then it's, what is it? 8 is T8, is T0. And if it's 16, then it's S0. And then these 5 bits for a shift amount, this is called shift amount. I'm not gonna, it's not important right now, but it's if it's the shift command. You know the shift command? You have to know the shift command. It exists in C++. You know what shifting is? You learned that in digital systems.
Oh,
Shifting right, left. So there's actually a command to do that. I can shift stuff right and left. So the shift amount is if the opcode tells me that it's a shift command, right or left, then how much do I want to shift? And that goes in this 5 bits over here. Why 5 bits? Because this maximum I'm going to do is shift everything off. That's 5. That would be 31 shifts.
If you try to shift number starting from 2, 31 times, is it back to 2?
No, they shift and they go off into the abyss.
So now it's all 0.
Yes. If I shift 32 or 31 bits, then
They're gone.
they're all gone. Well, we're going to learn there's some clever things you can do with shifting.
Okay.
For example, what is 1 shifted left? 2. What is 1 shifted left twice? 4. Every time I shift something left, I double it. So if I want to multiply by 4, instead of using the multiply command, I can save time. See, multiplying is actually a very complicated process. You have to add and add and add and add and add. So if I want to multiply by 32, all I do is shift 5, and I did it. And it's much faster than actually multiply.
So then this whole thing, before you said it was adding 0 and 32. So since it's 0, you know that it's not.
I didn't quite get the question, but yes, if this is a 0, then it's an R type.
What does 0 mean?
It just means it's an R type. How do I know that it's actually an add command? That's the big question. So that's what the last field here is, the function command. The function section is for the actual command. So you see over here, I wrote 32 over here. Remember we said that 32 was 20 in hex? And that's for add. If we go back to that table,
Oh, it needs 6 bits.
it needs 6 bits. Well, we don't know why it needs 6 bits. It
Well,
just
you need to do 32 is there.
right. Yeah. So look, hex is add. Let's find subtract. You guys with me? Let's see if let's find subtract. Subtract here. Sub. Look, it's 0 on the left, so it's also an R type, but on the right, it's a 22, which is 34.
You need 6 bits. Oh.
So you need 6 bits. The question is why though, because you'll notice that there's almost like, I don't know if there's any command that's like, there seems to be holes. Whatever. Anyway, there's not enough. There are not 64 commands here. There's not enough. Anyway, whatever. Okay. So that's how you. This is a R type. Now wait a second. Let's go back to our example.
You don't have to go second, or you just read remember, or practically use them.
Well, no, this is very important. This is very important. You need to know that this concept that there are fields, it's going to affect the architecture because we need to access these fields. The hardware is going to need to go to the opcode and look at it, and it needs to know that it's 6 bits or 5 bits. Okay, look at this command. What's the difference between this command and the add command? In terms of format. In terms of format, what's the difference between this command, the LW, and the add? No, what? No, this is both, okay, the comments, I don't care. No, the format in the sense, if I'm gonna have to convert this. How many registers are in this one? How many registers are in this one? Bottom one has 3. That's R type. It's a register type. It has the most registers. This is not got 3. It's got only 2 registers. See that? S3 and T0. And then it's also got something else. A number just stuck in the middle of the command is a number, 32. Notice there's no numbers here. There's just registers.
That's true.
Here there's actually a number sitting there. Where am I going to see that number, and how big can that number be? How many bits can that number be? Can I put any number there? Is there a
What does
limit?
the number do?
Well, we know what the number does. We know that the number says add this 32 to that, and that's where your load word is going to go.
Right.
But how big is this number? Where does it go? It's obviously not going to work in the R format, because I might want to put a number there like 1,000, but it's not going to fit into 6 bits. So where am I going to put it? So I need a new format.
So our format is for commands like adding.
Is for any command that has 3 registers.
I didn't know.
That's why it's called the R type. That's the way I remember it. R type is the register type. It has many registers. Okay? So we need a new type for this one that has a number. Now we call this number when there's a number in the command itself, we call it an immediate value. Why do we call it an immediate value?
Didn't have to get it from the memory, so
Oh, very good. What's your name?
Shaman.
Shana. Shana says very nicely. Because it's immediately available to us. We didn't have to go running to a register and look at the register and see what number is there. It's immediately available. It's, in Hebrew, you'd say zamin. It's ready for us. Cash. It's cash in hand. As we say, mizumani. Kesed mizuman is it? It's zamin. It's ready. It's immediate. So guess what this other type, this format is called instead of R? I. Israel. It's the I type for the immediate type. And look at it. Here's that immediate value. It's over, and we set aside 16 bits for that number. That means the maximum value we can have is 32,000. Right? 2 to the 15, 2 to the 16, 2 to the 15 minus 1. You know about unsigned and signed? If it's unsigned, then it would be 2 to the 16th minus 1. But if it's signed, it would be 2 to the 15th minus 1, plus or minus.
Well, it helps us if there was a minus. Why is the number of 30?
I could add a number. I could go backwards. Yes, I could go backwards. Isn't that weird? In arrays in C++, you can only put a positive number. It can say index number 12. But what if I want to go to index number minus 12? You can't do that still. So here you could.
You could, because if you started from like,
Exactly. If you did pointer arithmetic, you could move along the array and then go back. So what?
you could add
Guys,
more or
it's
less.
weird.
It's weird. It's
So you
definitely
can
weird.
subtract from it.
But yes, you can go backwards in your. But remember, load word is just one command. There are other commands that we didn't learn yet that are also of the I type, for which a negative number is certainly reasonable. Okay, so now the R and the RS and the RT. Remember we called them RS and RT before? We're still going to call them RS and RT. See? RS and RT and RD. So the RS and RT stay where they are because they're physically located there. Those are the physical locations. But now we understand why it's called RT, because it's going to be the target. What do I mean by the target?
Where you would hang it towards.
Remember our load word? So here, wait a second. Here, I'm sort of skipping through these slides. You can look at them more, but here I wrote plus or minus 2 to the 15. Okay. So let's look at this command here. I'm going to say why it's a target. Look at this first load word here. First load word, what does the target mean? Target means loaded to where? Notice the 8 and the 9. What is the 8? 8 is, if you remember, 8 is T0. 9 is one more, is T1. Notice the order switches. Which is the target of this command? Load word means take this number and put it in T0. So T0 is obviously the target, where I want to put the number. So look where T0 goes, over here, in the RT field, the target. The RS is going to be the address of the array. And the 1,200 is how much to advance from that address forward, how many bytes. Now, if you remember, the original command was in C++ here that I'm translating is 300. And if you remember, 300, I got to multiply by 4 because we're going to talk in bytes, and assuming that this is a integer, that these are words, this is like floats maybe or ints. So 300 times 4 is 1200. So I write 1200. Now the 1200 is going to, these lines I couldn't figure out how to get rid of them in the slide. But imagine this 1200 is spread across this whole 16-bit section. It's not just stuck over here. It's spread across this whole 16-bit section.
What did the RD in the past do? Meaning we're skipping the RD.
Oh, the RD, notice the RD is not being used in the I command. It's all these are, here the RD is being used because here it's saying add register 18, the contents of register 18 to the contents of register 8, and put it in register 8.
That's
The
okay.
D is destination,
Okay, but you don't.
but that's the R type, right? That is the R type.
With
In the R type, the RD is relevant. This title here is only relevant to the R type. In the I type, this is irrelevant. This is all just the
Not even
immediate.
1200.
This 1200 is all this large area here called the immediate value.
Meaning it tells you very much straight away to add the.
Tells you that's the number to add to whatever is in the RS.
It's backwards.
Yeah, a little bit backwards. Remember, I said blame it on Gray's number. Yeah. Or don't, or blame it on the people who continue making chips the way they used to.
Sorry, do we get a break?
Why? No, we're gonna go to 4 in the afternoon.
No, just because we have a, I'm
supposed to have a
wondering
break?
how it works because we have this until 45, and then we have at 45 exactly another class in a different building.
You're right. Well, when do we start? At 10:15? So it should be what it should be. How many? It should be 2.5 hours, right? No. So well, I don't know. 10:15, 11:15, 12:15.
It's 2.5 hours.
That's a lot of hours.
Wait, no. It's supposed to be, no, what is it, 2.5 hours? It's supposed to be 2 hours and 15 minutes, right?
Right.
2 academic hours. So we start at 10:15, so 10:30. We should stop at 12:30. Really.
That's what I was wondering.
Yeah, I think we should stop at 12:30.
Because we don't get a break in between this class and the next.
Maybe
class.
next time, right? So we'll stop in another 10 minutes.
All right.
Okay.
Wait, are other classes in a different?
Yeah, it's fine. It's we're doing some.
Well, Joyce will let us eat for the first half of class.
Yeah.
Oh,
it's
you
fine.
guys are in math?
I don't think you can eat
Math
this.
is
She's
fine.
very strict about this. I don't know if they really let you.
What if we like get our knees and beg? I'm sure it'll be fine.
We need to eat. Right?
That's why.
Well, let me- You know what?
I think if we need to like, in general, 12:30 is.
We're at a very, we're almost at, I'll finish when we finish, okay? We're about to finish, so. When we
No,
finish-
no problem. Just enough time to eat.
Yeah, good.
15 minutes
Don't
is
forget,
great.
lunch
as long
is
as we can
at-
get
is at
some
1
lunch.
All right, guys, so let's
1:30.
just continue here.
Yeah, we have lunchtime. It's from 1:30 to 2. Standard class on the class.
So let's go through this, wait.
Oh, we usually don't say that. So
That might be official lunch. Wait, so we.
But no, I wanna continue.
Yeah, break for 1:30.
But I tried to.
At least there should be. Instead.
Okay. Look at this, let's look at this slide. This is an important slide.
Usually a break there.
We sort of looked at it haphazardly. Let's look at it more systematic. This is the command in C++. My array at place 30 equals H plus my array at place 30. So basically, I'm
My array plus H. You're meaning you're adding H to.
I'm
whatever
adding
value.
H to whatever in my array at 300, and I'm putting it in the same place. I can put it in a different place, I'm putting it in the same place. So how are we gonna do that in MIPS? So it's gonna be 3 lines. First, we're gonna have to grab whatever is in this location, 300 of my array. So I change the 300 to 1200. I take T1, assuming that T1 is my pointer to my array. I mean, I didn't explain how that happens. And then I'm going to add it to T0, which I'm assuming is my H. No, sorry, I'm going to just load it. Sorry. First thing I have to do is wheel it into the, to the surgery room. I'm just going to load it into temporary variable 0. Now I got the value. That was just to get the value in this location. I retrieved it from this location. That's just this part of the command. I didn't yet do the plus. Now I'm going to do the plus H. Now I'm going to say, take that T0, which I loaded from memory into a register, and add that register to S2, which I'm assuming is got my H in. Now I wrote here in a comment, S2 is register number 18, which we saw. Remember, S0 is 16, so 17 is S1, S2 is.
That hashtag symbol means the comment.
Oh yeah, that's how you make comments in assembly, the hashtag.
just so many symbols to keep track of, and they mean different things every.
Yeah, well, I'll get used to it. There's a certain set of languages where the hashtag is common. And assembly and also scripting languages. If you do like PHP. I think PHP. Actually, does anyone know PHP here? I don't remember. But in script, guys, just you're thinking of doing art therapy or computer science. You just
Yeah, I was thinking about literature. Computer science and letter science. Keep on the floor.
what? Okay, let's go back to our work here. So add. So I'm taking this number and I'm putting it into T0. So far, what I did was I grabbed it. The first line I grabbed this. The second line I took that number T0 and I added to the H and I put it back into T0. So now my T0 has this value. I now have to copy this value into the array with store words. So T0 into 1200 of the same pointer. So I'm going to translate that now into assembly. And I'm going to write 35 is the opcode for load word. How do I know that? Load word. Anyone see load word here? Store word. Load here. Load byte.
It's under load.
There. Load word. See it? LW. Look what it says. 23. What's 23? Well, 20 is 32 plus 3 is 35. So that's how I got 35 as the opcode. In the I type, the opcode you write in. Remember, in the R type, you put a 0 and you put the opcode, you put the function in the function field, you put the opcode. All that's from the table. And 43 is obviously store word. And then I just put the 9 is the RS, is the source. Why is that the source mean?
The computer's doing behind it, but we're not ready for it.
This is what the assembler is doing. And you're going to do this on the exam.
We're not going to write $NW $0 instead of writing 4029.
No, the exam is going to say convert these 3 lines into assembly, into machine language. And you're going to write this.
In decimal means machine language?
In decimal, yes.
Is it all?
Well, wait a
multiple choice
second.
or writing?
What?
We're writing this or it's multiple choice?
I don't know. Either. Could be either.
I thought we're only learning from 60 and
No.
not
But it's important to know. Okay. What's the 9 here referring to? What's the 9 referring to? It's the T1. Why is the T1 over here? Why? Because that's the source. That's the source where I'm getting it from, and I'm loading it into the T0. So that's the target. That's the 8. And the numbers here. Look at the store word. Store word. What's the what?
So then you're putting it back.
Yeah. But it's a little bit confusing because look, this is still the RS. The store word, the 9 stays the. Sorry, wait a second. Look, this is the first thing, right? And it goes here. This is the first thing, and it goes here. So why is that the target? It doesn't really make sense. It's not really the target. The target, I'm trying to put it in here. But that's just the way we continue calling it that way. It always switches. The point is, the order here stays the same, and it switches in here, always. In other words, I always write, whether I'm doing load word or store word, I always write the register that I'm talking about, not the address first. And the address is second. Always register, address, register, address. And when I write it over here, I always write the address first. Notice the T9 is this, the address first. It's always going to add this one to this one. So also here I write this one to this one. And then the 8, and then here's my add command, and 18 is again, I do these 2 first. So 18 is the S2, then the 8 for the T1, and then the T0, this one is over here, backwards.
Can you do a full example of it, like on the board? Like here, we get this, and then we do this, and now from here, we're trying to store it into here. So we're gonna go through this. Can we do like one? I mean, I know it's the same here, but now we can see it instead. I know it's also.
Yeah, I agree with you, but I want to
We
end.
see
I want to
our
end
teachers,
now.
see
I want
them
to
do
end.
next class.
Wait.
Do it next time.
Yeah.
Yeah, we can do this stuff. But wait, let me just. I want to show you one more slide. Because now look at this number. What's 35? 35 is a bunch of ones and zeros, right?
Right.
I understand.
What's 9?
Oh, that's 32.
Look at this. You add this all up, 32 bits.
Hey.
Now we've got to assembly. We've got from assembly to machine language in bits. And look, here's a 0. Why did I write all these zeros? Because it's got to be 6 bits. It's got to be 6 bits. That code. So I didn't just write 1 0. I read all the zeros. And this, what's this number here? What's this number? What? Wait a second. What's this number here? Sorry, this number. That's 1,200. That's my immediate.
So all those people that were that you were gonna split from the 5 now.
So now you can just write in ones and zeros, and you'll much more fun. All right, we'll stop here.